Okay, hello everyone in a new video. So we have reached part 3 of chapter 11, which is the chapter of pressure and liquids in the third unit of mechanics. Then in this one we are going to solve some exercises related to what we have explained previously in parts 1 and 2. Then exercise number 4, consider a tube containing a certain amount of water, document 1. So they mentioned this document, now we can use it. Given the atmospheric pressure P atmosphere is equal to 76 centimeters of mercury. So notice that here the quantity, which is the pressure, is not in agreement with the unit, which is centimeter, because we know that the unit of the pressure is either Pascal or in Newton per meter square in the SI, whereas centimeters represent the unit of length or height. Then from the early beginning we need to rewrite this properly. So since this value carries the unit centimeter, then it represents the height. And because it's related to the atmospheric pressure, then this value represents the atmospheric height. So the atmospheric height is given by 76 centimeters. Moreover, knowing that centimeter is not the SI unit of length, in order to convert from centimeters to meters, we simply divide by 100. Then 76 divided by 100. Then in this case, the atmospheric height is given by 0.76 meters. Okay, density of mercury is given by 13,600 kilogram per meter cube, and G is equal to 10 newtons per kilogram. Let me write here that the density of mercury is given by 13,600 in the SI, and the G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Number 1, okay. Notice that till this moment they didn't mention anything about document 2, then we are not allowed to use it. Number 1, referring to document 1, 1.1, the two free surfaces of water are at the same horizontal plane, justify. So always such type of questions are answered using the rule of 3, which is given by same pressure, same liquid at equilibrium. And either we say same pressure or same horizontal level. So since we are interested in justifying why the points A and B, the two free surfaces of water, they are given by A and B, we are interested in justifying why they are at the same horizontal level, then we will eliminate this, and our answer will be same liquid at equilibrium and submitted to the same pressure. And notice that indeed A and B are in the same liquid. In this case this liquid is water, and it is for sure at equilibrium and the same pressure. Why same pressure? Notice that the points A and B, both of them are open to the atmosphere, then they are submitted to the atmospheric pressure. Then let's say, since, okay, here the two free surfaces of water are given by A and B. Since A and B are in the same liquid, at equilibrium and submitted to the atmospheric pressure, then A and B are in the same horizontal level. This is part 1.1 of part 1. Now 1.2, calculate in Pascal the value of the pressure at A and that at B. Because A and B are, both of them are submitted to the atmospheric pressure, then in other words we need to calculate this pressure, which is given by the atmospheric pressure. So here The atmospheric pressure is equal to 76 centimeters of mercury, which means that it is related to a liquid, and it is the pressure due to a liquid which is given by the density of the liquid, rho L, multiplied by G multiplied by H. And here the liquid is mercury, so it's the density of mercury multiplied by the value of G and multiplied by the depth or the height. Which height? In particular the atmospheric height, since we are calculating the atmospheric pressure. Now the density of mercury in the SI is given by 13,600, and the value of G is given by 10, and the value of the atmospheric height is given by 0.76. Now plugging this on the calculator, then the value of the atmospheric pressure is given by 103,360. Since all of these quantities are expressed in the SI, so the value of the atmospheric pressure will be in the SI, which is Newton per meter square, and this unit is usually denoted by Pascal. Then the atmospheric pressure is given by 103,360 Pascal. And let me write here that the atmospheric pressure is given by 103,360 Pascal. Now number 2, we want to determine the density rho prime of a certain liquid L that doesn't mix with water. For this reason, we pour in branch 1 of the tube an amount of oil to height H is equal to 20 centimeters. Then H is equal to 20 centimeters. Knowing that also centimeters is not a unit of length, in order to convert from centimeters to meters, we divide by 100. Then 20 divided by 100, so H is equal to 0.2 meters, and of density rho is equal to 900 kilogram. So this density is that of oil. Let me make some space here. So the density of oil is given by 900 kilogram per meter cube. And in branch 2, a certain amount of L of height to a height H prime is equal to 16 centimeters. Then H prime is equal to 16 centimeters, also dividing this by 100 to convert it to the SI. So it's equal to 0.16 meters. The surfaces of separation water, oil and water liquid are at the same horizontal plane. Document 2, they mentioned document 2, now we can use it. So what's happening here is the following. This is the branch 1. We have poured in branch 1 a certain amount of water, such that a certain amount of oil, sorry, so this is water. Then here in this branch we have poured water. We have poured oil, and this is water. So this is oil here. And here we have that the height of oil is given by 0.2 meters. And in the other branch, which is branch number 2, we have poured a certain amount of liquid of L. We don't know the nature of this liquid, to a height H prime. The value of H prime and the SI is given by 0.16 meters. Knowing that in this case the points A and B are in the same horizontal level. So this is the first surface of separation between oil and water, and this is the second surface of separation between water and this liquid. And they are telling me the surfaces of separation water, oil, water, liquid are at the same horizontal plane. Document 2. Now 2.1. Determine in Pascal the value of the total pressure at A. So we are in document 2. Whenever we are interested in determining the pressure at a certain point, we look upward. So notice that the point A is submitted to two pressures, the pressure due to oil and to the atmospheric pressure. And here they are telling me to calculate the total pressure. So we need to determine the pressure due to oil and added to the atmospheric pressure that we have already calculated. But first we need to mention that A is submitted to the pressure of oil and to the atmospheric pressure. So usually they give half a mark for this statement. Now we can say that the total pressure at the point A is equal to the pressure due to oil plus the atmospheric pressure. And because the pressure due to oil is pressure due to liquid, so it's given by the density of the liquid times G times H. So the density of oil is given by rho, is denoted by rho, multiplied by G multiplied by the depth at which we are calculating this pressure, which is denoted by H, plus the atmospheric pressure. Now the density of oil in the SI is given by 900. The value of G is given by 10. And the value of H is given by 0.2. And we have already calculated the atmospheric pressure, which is given by 103,360. Now plugging this on the calculator, so it will be given by 1,800 plus 103,360. Now plugging this on the calculator, then the value of the pressure at the point A is given by 105,160. Since both of these values are expressed in the SI, which is Pascal, so the unit of the pressure at the point A will be expressed in Pascal as well. Or in Newton per meter square, it's the same. So the pressure at the point A is given by 105,160 Pascal. So here let me write that the total pressure at the point A is given by 105,160 Pascal. Now in 2.2, deduce in Pascal the value of the total pressure at B, and by deduce it means that we need to use the previous part. In part 2.1 we have determined the pressure at the point A, so using this we need to determine the pressure at the point B, and noticing that the points A and B are in the same horizontal level. So let's use the rule of 3 in order to deduce the pressure at the point B. So the rule of 3 says the following: same liquid at equilibrium, and either we say same pressure or same horizontal level. Since we are interested in justifying why the pressures at the point A and B are equal, because they mentioned deduce, then we will eliminate this and our answer will be same liquid at equilibrium, same horizontal level. So they are in the same horizontal level because they mentioned so in the given. So this is okay, for sure it is at equilibrium. And now let me make it clear why they are in the same liquid. So as we have said previously, whenever we are interested in justifying or determining the pressure, we look upward. But whenever we are interested in determining whether this point it is in which liquid, we always look downward. So looking at the point A downward, we notice that below it there is water, and looking at the point, so it is in water, and at the point B looking downward we can see that there is water, so it is in water. Therefore both of them, A and B, are in water, although above the point A we have oil and above the point B we have the liquid L. But whenever we are interested in determining whether a point it is in which liquid, we always look downward. So the points A and B are in water. Now in 2.2, so let's say first the justification that since A and B are in the same liquid, which is in this case water, at equilibrium, and in the same horizontal level, then A and B are submitted to the same pressure, which means that the pressure at the point B is equal to the pressure at the point A, which is equal to 105,160 Pascal. Now in 2.3, give the expression of the total pressure at B as function of rho prime. So we are interested in determining the pressure at B, so the total pressure at the point B. Since we are interested in determining the pressure, so from the point B we look upward, we notice that the point B is submitted to two pressures. The pressure due to this liquid, which is liquid L, and to the atmospheric pressure. Then first let's say that B is submitted to the pressure of the liquid, and to the atmospheric pressure. So they usually give half a mark for this statement. Then the pressure at the point B is equal to the pressure due to this liquid, which is denoted by PL, plus the atmospheric pressure. Since this pressure is the pressure due to a liquid, so it's given by the density of the liquid multiplied by G multiplied by the height. The density of this liquid is denoted by rho prime multiplied by G multiplied by the depth at which we are calculating this pressure, which is denoted by H prime, plus the atmospheric pressure. So notice that here they are telling us give the expression of the total pressure at B as function of rho prime. Then we must keep rho prime as a variable, knowing that we are interested in determining PB, the pressure at B. Then rho prime, keeping rho prime as a variable, multiplied by G, the value of G is given by 10, the value of H prime in the SI is given by 0.16, plus the atmospheric pressure, which is given by 103,360. Then 10 multiplied by 0.16 is given by 1.6 rho prime. So here it is 1.6 multiplied by rho prime, plus 103,360. So the pressure at the point B is given by 1.6 rho prime plus 103,360. So notice that for the value of PB I didn't include any unit since it is expressed in terms of another variable. So it happens sometimes in physics that the quantity doesn't include any unit. So here it is more convenient that we don't include any unit for the pressure at the point B, simply because of the following reason, since it is expressed in terms of another quantity. Now in 2.4, deduce the value of rho prime, and by deduce it means that we need to use the previous part. In the previous part we have determined the expression of the pressure at the point B as function of rho prime, and we already know the numerical value of the pressure at the point B, which is given by, so here we have deduced that the pressure at the point B is given by 105,160 Pascal. So we know the numerical value of the pressure at the point B, and we have the expression of the pressure at the point B in terms of rho, and knowing that we are interested in determining the value of rho prime, so we need to find an equation which includes rho prime, so a linear equation. Then in this case the equation is given by PB is equal to PB. So on the left hand side we know the expression of PB in terms of rho prime, which is given by 1.6 rho prime plus 103,360, And on the right hand side, we know the numerical value of PB, which is given by 105,160. Now in this case, we have obtained a linear equation and one unknown. The unknown is rho prime. So how do we solve this equation? We put rho prime on one side and all the other numbers on the other side. So now dragging this number to the right hand side, it will gain a minus sign. Then 1.6 rho prime is given by 105,160 minus 103,360. So 1.6 rho prime is equal to, now plugging this on the calculator, then it's given by 1,800. Let me make some space here. Then 1.6 rho prime is equal to 1,800. Recall that we are interested in determining the value of rho prime. Here we have determined the value of 1.6 rho prime. In order to get rid of 1.6, we divide both sides by 1.6. Then we have that rho prime is equal to 1,800 divided by 1.6. Plugging this fraction on the calculator, then the value of rho prime is given by 1,125. Since all of these quantities are expressed in SI, so the value of rho prime will be expressed in SI, which is given by kilogram per meter cube. Then the density of this liquid is given by 1,125 kilogram per meter cube. And notice that here there is something wrong in this exercise. Why? So the density of oil in this case is given by 900 kilogram per meter cube. And the density of water is given by 1000 kilogram per meter cube. So oil is floating on the surface of water, so this is reasonable since the density of oil is less dense or is less than the density of water. But however, as for the liquid L, we have determined the density of this liquid and it's given by 1,125 kilogram per meter cube. And comparing this density with the density of water, so this liquid is more dense than water, which means that this liquid will not float on the surface of water. So the water will float on the surface of this liquid. So there is something going wrong in this exercise, but however our calculation is correct. We are sure of our calculation. So the structure of this question is wrong. And now let's move to the next exercise. Exercise number 5. Given atmospheric pressure P atmospheric is equal to 76 centimeters of mercury. So here we need to be very careful. Notice that the quantity and the unit in this case are not in agreement, since the pressure has unit in the SI given by Newton per meter square or Pascal, whereas the centimeter represents the unit of length or height or depth. Then from the early beginning we need to rewrite this properly. So notice that this value has the unit centimeters, which means it represents the height, but which height? Since it's related to the atmospheric pressure, then it represents the atmospheric height. So let's write that the atmospheric height is equal to 76 centimeters of mercury. Knowing that also centimeters is not the SI unit of length, in order to convert from centimeters to meters, we simply divide by 100. Then 76 divided by 100, then the atmospheric height, and the SI is given by 0.76 meters. Moreover, the density of mercury rho Hg is equal to 13.6 grams per centimeter cube. Knowing that gram per centimeter cube is not the SI unit of density, in order to convert from a gram per centimeter cube to kilogram per meter cube, we simply divide by multiply by 1000. Then 13.6 multiplied by 1000, this is equal to 13,600 kilogram per meter cube. And the density of water, raw water, is equal to 1 gram per centimeter cube. So knowing that a gram per centimeter cube is not the SI unit of density, in order to convert from gram per centimeter cube to kilogram per meter cube, we simply multiply by 1000. Then 1 multiplied by 1000. Then the density of water is given by 1000 kilogram per meter cube. and the G is equal to 10 newtons per kilogram, which means we are performing this experiment on the surface of Earth. Part 1, atmospheric pressure. We consider a YouTube containing water at equilibrium, document 1. Then they mentioned document 1, now we can use it. Notice that till this moment they didn't mention anything about document 2, then we are not allowed to use it. Number 1, so we are in part 1, number 1. The 2 points A and B are submitted to the same pressure, which is the atmospheric pressure. So notice that because we are interested in the pressure, so we always look upward. Notice that the points A and B are open to the atmosphere, so they are subjected to the atmospheric pressure. They are asking me to calculate in Pascal the value of this pressure. So the atmospheric pressure, as in the given here, they are telling me it is equal to 76 centimeters of mercury. So it's the pressure due to a liquid which is given by mercury. So it's the density of this liquid times the G times H. So the density here is given by the density of mercury. Since they are telling me it's equal to 76 centimeters of mercury, times the value of G, times the height, but which height? The atmospheric height, which allows us to calculate the atmospheric pressure. Now the density of mercury is given by 13,600, multiplied by G, which is given by 10, multiplied by the atmospheric height, which is given by 0.76. Plugging this on the calculator, then the atmospheric pressure is given by 103,360. Since all of these quantities are expressed in the SI, so the value of the atmospheric pressure will be in the SI, which is Newton per meter square. And this unit is usually denoted by Pascal. Then the atmospheric pressure in this case is given by 103,360 Pascal. And notice that here they are telling me to calculate the value of this pressure in Pascal. So the atmospheric pressure is given by 103,360 Pascal. Now in number 2, the 2 points A and B are in the same horizontal plane. Justify. So here the dotted line represents or indicates that the 2 points A and B are in the same horizontal plane, and always such type of questions are answered using the rule of 3, which is given by same liquid at equilibrium, and either we say same pressure or same horizontal level. Since we are interested in justifying why the 2 points A and B are in the same horizontal plane, then we will eliminate this, and our answer would be same liquid at equilibrium and same pressure. Then let's say in number 2 that since A and B are in the same liquid, they are in the same liquid because both of them are in water. So this liquid represents water at equilibrium for sure. And submitted to the same pressure, which is the atmospheric pressure, and submitted. Then A and B are in the same horizontal level or horizontal plane. And now part 2 of this exercise, density of liquid. In one of the 2 branches of the same YouTube, we put a quantity of liquid immiscible with water of density rho. At equilibrium, the height of the liquid is H is equal to 20 centimeters. So knowing that centimeters is not a SI unit of length, in order to convert from centimeters to meters, we simply divide by 100. Then 20 divided by 100. Then the height H is given by 0.2 meters. And that of water above the surface of separation of the 2 liquids is H1 is equal to 16 centimeters. Knowing that centimeters is not the unit of length, in order to convert from centimeters to meters, we divide by 100. So h1 is given by 0.16 meters. And they mentioned document 2. Now we can use it. So this liquid, which is shaded horizontally, is given by water. And this is another liquid of density rho that we wish to determine its density. The value of h is given by 0.2 meters in the SI, and the value of h1 is given by 0.16 meters. Now here what we have done, we have poured in this branch a certain amount of this liquid of density rho, now such that the points C and D are in the same horizontal level as shown here, and the height of this liquid is given by 0.2 meters, and for sure that this liquid is immiscible, that doesn't mix with water. Immiscible means that it doesn't mix with water. Okay, now we need to determine the value of rho. So first let me mention this. We know that the density of water is given by 1000 kilogram per meter cube. So notice that this liquid floats on the surface of water, which means that the expected value of rho must be less than 1000. Now number 1, determined in terms of rho. Let me make some space here. So we are in part 2. Number 1. So for sure it is at equilibrium. Number 1, determine in terms of rho the pressure at the point C, and here by the pressure they mean the total pressure. So it's not the pressure due to the liquid nor the pressure due to the atmosphere, but however the sum, which is the total pressure. So because we are interested in determining the pressure, we consider the point C, which is the pressure at the point C, and we look upward. Notice that the point C is being submitted to the pressure due to this liquid and to the pressure at the point A, which is the atmospheric pressure, and it is being transmitted to the point C according to Pascal's theorem. So first let's state that C is submitted to the pressure of the liquid. And to the atmospheric pressure. So they usually give half a mark for this statement. This statement is important. So the pressure at the point C is equal to the pressure due to the liquid. So let's denote this pressure by PL plus the atmospheric pressure. Now the pressure due to liquid is given by the density of the liquid times G times the depth at which you are calculating this pressure. So the density of this liquid is denoted by rho times G times the depth, which is denoted by H, plus P atmospheric. So notice that in this case they are telling me in terms of rho, so we need to keep rho as a variable. Moreover, we don't know the value of rho. So rho times the G, the value of G is given by 10, the value of H is given by 0.2, plus the numerical value of atmospheric pressure, which is given by 103,360. Now 10 multiplied by 0.2 is given by 2 rho, so here 2 multiplied by rho, plus 103,360. So the pressure, the total pressure at the point C is given by 2 rho plus 103,360. So notice that I didn't include any unit for the pressure at the point C, since it's simply expressed as a function of another variable. So it's more convenient to not include any unit. Then here let me write that the pressure at the point C is given by the double of rho plus 103,360. Now calculate the pressure at the point D, and since here they are telling me calculate, and they didn't mention anything about in terms of another variable, so we need to calculate the numerical value of the pressure at the point D. And here for sure by the pressure they don't mean the pressure of the liquid nor the pressure due to the atmosphere, but rather the sum, which is the total pressure. So notice that here whenever we are interested in the pressure, we consider the point and we look upward. Notice that the point D is being submitted to the pressure due to this column of this liquid and to the atmospheric pressure, which is being applied to the point B and transmitted to the point D according to Pascal's theorem. So let's say first that D is submitted to the pressure. So this shaded liquid is given by water. So let's say this is submitted to the pressure of water and to the atmospheric pressure. So as we have said, this statement is important and they usually give it half a mark. So the total pressure at the point D is given by the pressure due to water plus the atmospheric pressure. Now since water represents a liquid, so it's the pressure due to liquid, which is given by the density of the liquid times G times H. The density of this liquid, which is water, is given by rho water times the G times the depth at which we are calculating this pressure, which is noted by H1, plus the atmospheric pressure. Let me make some space here. So the pressure at the point D, which is equal to the density of water, which is 1000 in the SI, multiplied by the value of G, which is 10, multiplied by H1, which is given by 0.16, plus the numerical value of the atmospheric pressure, which is given by 103,360. Now plugging this on the calculator, then it's given by 1600 plus 103,360. Now plugging this on the calculator, then the total pressure at the point D is given by 104,960. Since everything is expressed in the SI or in Pascal, so the value of PD will be in Pascal. So the total pressure at the point D is given by 104,960 Pascal. And now in number 3, the pressure at C and the pressure at D are equal. Why? So the pressures at the point C and D are equal, and this always can be justified using the rule of 3, which is given by same liquid at equilibrium. And either we say same pressure or same horizontal level. Since we are interested in justifying whether they have the same pressure, we will eliminate this. Then our answer will be same liquid at equilibrium, same horizontal level. They are in the same horizontal level because they indicated this in the document, and for sure it is at equilibrium as they mentioned here in the given. Now they are in the same liquid. Why? So notice that the point D is in water, because above the point D and below the point D is in water. However, C is also in water, although above the point D there is liquid, but always whenever we're interested in determining the point C in which liquid it is, we always look downward. So considering the point C and looking downward, we can notice that below the point C there is water, so it is in water and not in this liquid L. So let's say that since C and D are in the same liquid, at equilibrium, and so here the same liquid is water and in the same horizontal level, then C and D are submitted to the same pressure. So the pressure at the point C is equal to the pressure at the point D. And here let me write that the pressure at the point D is given by 104,960 Pascal. And let me correct this, that this is part 4. Now deduce the value of rho and by deduce it means that we need to use the previous part. In the previous part we have stated that the pressure at the point C and the point D are equal, so let's use it directly. Now in order to find the value of rho, we need to find a linear equation and one unknown, and this unknown is given by rho. So the pressure at the points is given by 2 rho plus 103,360, and the pressure at the point D, which is given by the numerical value 104,960. So this is a linear equation and one unknown. The unknown is given by rho, which you are interested in determining. So how do you solve this such type of equations? We put rho on one side and all the other numbers on the other side. So dragging this number to the right hand side, then 2 rho is equal to 104,960 minus 103,360. Now plugging this on the calculator, then 2 rho is given by 100,600. Then we have that 2 rho is equal to 1,600. But notice that we are interested in determining the value of rho and not 2 rho, then dividing both sides by 2. Then the value of rho is given by plugging this fraction on the calculator. Then rho is given by 800. Since everything previously is expressed in the SI, so the unit of rho will be expressed in the SI, which is given by kilogram per meter cube. And now let's move to the next exercise, which is given by exercise number 6. The object of this exercise is to determine the pressure of a confined gas. For this, we consider a gas bulb having a closed tap R and filled with a gas. So here, this is a tap R. We can open and close this tap, and the confined gas is found inside this glass bulb. Okay, filled with a for this, okay, a rubber tube connects the glass to a Utube manometer. So this glass bulb is connected to a Utube manometer. This is the Utube manometer. This manometer contains water in equilibrium. The surfaces of water in the two branches are at the same level. So notice that till this moment they didn't mention anything about this figure, but I referred to it in order just to explain the glass bulb and the Utube. So given that the atmospheric pressure P atmosphere is equal to 76 centimeters of mercury, and here we need to be very careful, because notice that the quantity and the unit are not in agreement. This is the pressure, which has the unit Newton per meter square or Pascal, whereas centimeter represents the unit of height or length. So from the early beginning, we need to rewrite this properly. So since this value carries the unit centimeter, so it represents the height, but which height? Since it's related to the atmospheric pressure, then it represents the atmospheric height. Now, knowing that centimeter is not the SI unit of length, in order to convert from centimeters to meters, we simply divide by 100. Now the density of mercury is given by 13,600 kilogram per meter cube, and the density of water is given by 1000, and the value of G is given by 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. Now we open the tap R. We notice that at equilibrium the difference in the levels between the surfaces of water is 10 centimeters. See the figure. So now they mention the figure, then we can use it. So previously, before opening the tap R, the points B and A were in the same horizontal level. So this is the point B and this is the point A. Now after we open the tap R, so now the confined gas exerts a pressure at the point B, and now the point A rises above the points B and C up to a height given by 10 centimeters. So let's denote this height to be H is equal to 10 centimeters. Knowing that centimeters is not a unit of length, in order to convert from centimeters to meters, we divide by 100. Now number 1, determine in Pascal the value of the pressure exerted by air at A. By air, so they mean the atmospheric pressure. So notice that because we are interested in calculating the pressure, then we consider the point, which is A, and we look upward. So notice that A is open to the atmosphere, then A is being subjected to the atmospheric pressure. So let's say that A is submitted to the atmospheric pressure. So in this case, this statement is not important because here they are already telling me that the value of the pressure exerted by air, and by air means the atmospheric pressure. Now, so the atmospheric pressure, here they are telling me that the atmospheric pressure is equal to 76 centimeters of mercury. So it's the pressure due to a liquid, which is given by the density of this liquid times G times H. Which liquid? It's given by mercury of density ρ1 multiplied by the value of G multiplied by height. But which height? Since we are calculating the atmospheric pressure, so it is the atmospheric height. The density of mercury is given by 13,600. The value of G is given by 10, and the value of the atmospheric height in the SI is given by 0.76. Plugging this on the calculator, then the atmospheric pressure is given by 103,360. Since all of these quantities are expressed in the SI, so the value of the atmospheric pressure will be in the SI, which is Newton per meter square, and this unit is usually denoted by Pascal. So the atmospheric pressure at the point, is given by 103,360 Pascal. Now in number 2, calculate the value of the pressure exerted by water at sea. So notice that because we are interested in determining the pressure, then we consider this point, which is the point C, and we look upward. Notice that the point C is being submitted to two pressures, the pressure due to this layer of liquid and to the atmospheric pressure. Here they are telling me only to calculate the pressure exerted by water at sea, so the pressure only due to this layer of liquid. So no need to say that C is being submitted to the pressure of the liquid. So directly we can calculate the pressure at the point C due to water. Let's denote this pressure by PW, which is equal to the density of this liquid, which is density water, and it's denoted by ρ2, times the G, times the depth at which we are calculating this pressure, which is 10 centimeters, and this is denoted by H, which is equal to 0.1 meters. Now ρ2 is equal to 1000. The value of G is given by 10 and H by 0.1. Plugging this on the calculator, then the pressure due to water at the points is given by 1000. Since all of these quantities are expressed in the SI, so the value of the pressure will be in the SI, which is Newton per meter square, and this is usually denoted by Pascal. So 1000 Pascal. So PW is equal to 1000 Pascal. Now in number 3, deduce the value of the total pressure at sea. This is important, and by deduce it means that we need to use the previous part. In the previous part we have determined the pressure due to water, and also have determined the atmospheric pressure, knowing that at the point C is being submitted to the pressure due to this layer of liquid and to the atmospheric pressure which is being applied at the point A and transmitted to the point C according to Pascal's theorem. Then let's say C is submitted to the pressure of water and to the atmospheric pressure. So now in this case this statement is important, and they usually give it half a mark. Then the total pressure at the points is given by the pressure due to water plus the atmospheric pressure. The pressure due to water is given by 1000, and the atmospheric pressure is given by 103,360. Plugging this on the calculator, then the total pressure at the points is given by 104,360. Since both of these are expressed in Pascal, then the total pressure at the point C will be in Pascal, which is the SI unit. So the total pressure at the points is given by 104,360 Pascal. And here let me write that PC is equal to 104,360 Pascal. Now 4.1, B and C are under the same pressure. Why? So always such type of questions are answered using the rule of 3, which says or states that same liquid at equilibrium, and either we say same pressure or same horizontal level. Since we are interested in justifying why that B and C are under the same pressure, so we will eliminate this and our answer would be same liquid at equilibrium, same horizontal level. Indeed, this experiment is being performed at equilibrium. They are in the same horizontal level as this dotted line indicates, and they are in the same liquid, which is given by water. So this shaded liquid is water. So let's say that since B and D are in the same liquid, at equilibrium, and submitted and in the same horizontal level, sorry. Then B and C are submitted to the same pressure. So the pressure at the point B is equal to the pressure at the point C. For point 2, deduce then the value of the pressure of the confined gas. And by deduce, it means that we need to use the previous part. In the previous part, we have stated that the pressures at the point B is equal to the point C. So we need to use this relation, knowing that we know the value of PC, so we know the value of PB. But what does the total pressure at the point B represent? Notice that if we consider the point B and we look upward, above the point B we have only the confined gas and it's not submitted to the atmosphere. So the total pressure at the point B is considered to be the confined gas. So let's write that B is submitted to the pressure of the confined gas. So this statement is very important and they usually give it half a mark. So if we determine the pressure at the point B, we are done because now the pressure at the point B represents the pressure of the confined gas. But however, we know the equality between the pressures point B and C, or let's say, but the pressure at the point C is given by 104,360 Pascal. Then in this case, the pressure at the point B, which represents the pressure of the confined gas, is given by 104,360 Pascal. So this value represents the value of the confined gas. And by this we have finished solving this exercise. So that's it for me in this video, guys. In the next part, we'll complete the explanation of this chapter.